Welcome to Raw History. Here we cut through romanticization and speculation to show you the unfiltered reality of human history. Claims about sophisticated ground heat pipe systems in World War II bunkers that kept soldiers warm without fuel consumption, well, they present an appealing narrative about forgotten sustainable technology. But honestly, the reality proves less dramatic, but actually more interesting. Underground bunkers did benefit from ground temperature stability, but this was thanks to passive insulation from being buried, rather than engineered geothermal systems with circulating pipes. Understanding what actually kept World War II bunkers habitable reveals both the genuine advantages of underground construction and, the limitations soldiers faced in these cramped, often uncomfortable spaces. The ground temperature at depths where World War II bunkers were constructed remains relatively constant year-round. Below 6 meters depth, the undisturbed ground temperature is consistently at the mean annual air temperature. In temperate European climates, where most Western Front bunkers existed, subsurface temperatures generally range around 10 to 12 degrees Celsius, or about 50 to 54 degrees Fahrenheit. This thermal stability means underground spaces avoid the extreme temperature swings experienced at the surface, providing natural insulation that reduces heating requirements compared to above-ground structures. World War II bunkers benefited from Earth's thermal properties through simple physics rather than sophisticated engineering. The ground temperature distribution is affected by the physical properties of the ground, the local meteorological variables, and the surface cover. A common misconception depicts the Earth as a good insulator, when in reality the Earth has high heat conductivity. However, because Earth extends in vast areas, thermal energy loss transfers slowly, and temperature fluctuations lower with increment of depth. The heat capacity of soil is considerably higher than that of air, creating thermal inertia that stabilizes interior temperatures. Because of the high thermal inertia of the soil, temperature fluctuations at the surface of the ground are diminished as the depth increases. After reaching a specific depth, the soil's temperature is always higher than air temperature during winter and lower during summer. This passive benefit required no mechanical systems, pipes, or circulating fluids, just sufficient earth coverage to reach stable thermal zones. German bunker construction guidelines specified minimum soil coverage depths, partly to achieve this thermal advantage alongside structural protection and camouflage requirements. The thermal benefit came at a cost. During World War II, personal accounts describe spending many hours and sometimes whole nights in various underground bunkers. Many people dug them in their gardens at the start of the Blitz. They were never waterproof. Rain would seep in from underground, and occupants had to bail out water just about every time they used them. The combination of earth insulation with inadequate waterproofing and ventilation created damp, uncomfortable conditions that made underground shelter tolerable, but, honestly, far from pleasant. What actually provided heat? Most World War II bunkers relied on conventional heating methods when heat was needed beyond passive earth insulation. Wood or coal stoves provided the primary heat source in larger permanent installations, with chimneys carefully engineered to avoid creating visible smoke signatures that would reveal bunker locations. Smaller field bunkers and temporary shelters often had no heating systems at all, depending entirely on body heat from occupants, blankets, and the modest insulation provided by earth coverage. Electric heating appeared in some sophisticated command bunkers with generator power, but, fuel requirements for generators made this option available only to critical installations. The Atlantic Wall fortifications included some bunkers with electric heating powered by diesel generators that required constant fuel resupply. These represented the exception rather than the rule. Most soldiers occupying defensive bunkers endured cold, damp conditions that passive earth insulation merely made survivable rather than comfortable. Ventilation systems in World War II bunkers focused on providing breathable air rather than temperature regulation. Hand-cranked or electric blowers forced fresh air through intake pipes while expelling stale air through separate exhaust vents. This air exchange prevented carbon monoxide buildup from stoves and maintained oxygen levels, but it also introduced cold external air that unfortunately countered any passive warming from surrounding Earth. The engineering challenge involved balancing fresh air requirements against heat loss, with really no elegant solution available given the technological limitations of the era. So why didn't geothermal systems exist back then? Well, ground source heat pumps, which, actively circulate fluid through buried pipes to extract ground heat, weren't actually successfully implemented until the late 1940s. Robert C. Weber developed one of the earliest working examples, a homemade 2.2 kilowatt direct exchange system, but honestly, sources disagree on the exact timeline of his invention, placing it somewhere in the late 1940s after the Second World War ended. Now, Lord Kelvin invented the heat pump concept way back in 1852, and Heinrich Zoelli patented the idea of using it to draw heat from the ground in 1912, but practical implementation really had to wait for post-war technological development. The technical challenges that prevented Second World War-era geothermal heating systems included, first off, a lack of suitable piping materials and, well, the absence of efficient heat pump compressors small enough for bunker installation. Plus, the fuel requirements sort of undermined any sustainability advantage. Polybutylene pipe, which eventually made closed-loop ground source systems economically viable, wasn't actually developed until 1979. Before this material breakthrough, open-loop systems dominated, but these required suitable aquifers and created water management challenges that just weren't compatible with military bunker construction. Even if the technology had somehow existed, military logistics would have prevented widespread adoption. Installing buried pipe loops requires extensive excavation and, honestly, quite specialized equipment. The construction effort for a basic concrete bunker already strained resources on active fronts. Adding hundreds of feet of buried piping per bunker would have consumed time, materials, and labor that were better spent on other defensive priorities. So engineers focused on getting functional protective structures built quickly rather than optimizing long-term thermal comfort. The post-war geothermal revolution really took off as a result of the 1973 oil crisis, when ground source heat pumps became popular in Sweden, and since then have grown slowly in worldwide popularity as the technology has improved. Open-loop systems continued to dominate the market until the development of polybutylene pipe in 1979 made closed-loop systems economically viable. As of 2004, there are over 1 million units installed worldwide, providing 12 gigawatts of thermal capacity with a growth rate of 10% per year. This represents true geothermal technology that Second World War bunkers never employed. Modern ground source heat pump systems typically provide 3 to 6 units of heat for each unit of electricity used, achieving efficiency that honestly would have revolutionized Second World War bunker heating if it had been available. Contemporary installations use vertical boreholes, 100 to 400 feet deep, or horizontal trenches with precisely engineered pipe loops. These systems require professional installation and represent technology fundamentally different from the passive earth insulation that Second World War bunkers utilized. The payback period for residential systems is 2 to 10 years, while commercial systems achieve payback in 1 to 5 years. Economics that make sense for permanent installations but not for temporary wartime construction. Subscribe to Raw History for evidence-based explorations that separate historical facts from internet mythology, And share your thoughts on distinguishing real engineering from romanticized claims in the comments below.